Everyone, thanks so much for joining. And today I'm really delighted to have Anil, Seth, and Kameron Goold, our speakers for today on some early JWST results. And I'm delighted to introduce them to you. So Anil Seth got his bachelor's degree from Wesleyan University and then went on to get his PhD from the University of Washington. He then held postdoc fellowships at CFA and then went on to join a faculty position at University of Utah, currently a full professor. So he was the recipient of a highly competitive NSF Career Award and numerous AAG grants. I was really impressed to see, and he's also gotten numerous HST and ground-based observing proposals using cutting-edge adaptive optics instrumentation. And he recently received a hiely competitive medium program on JWST, which you'll get a first look at in today's talk. Anil's research centers around the centers of galaxies, and he addresses fundamental questions on black holes and the lowest mass galaxies, nuclear star cluster formation, mass, and the relationship to black holes. And I really think he's pushed the frontier in this field in obtaining the lowest mass dynamical mass measurements and limits in the lowest mass galaxies known in the universe. I've been really impressed that Anil has also been a dedicated teacher and mentor to numerous students and postdocs. He won a Teaching Excellence Award for his teaching at Utah. And he was also a visiting professor at Wellesley, I believe. And on top of all of this, he does numerous outreach activities I've been really impressed with. So I wanted to say that I've been really impressed by Anil. I think he's one of the kindest and most enthusiastic astronomers I've had the pleasure to meet. And really, it's been a joy to collaborate with him. And I also have been really impressed by how inclusive he is in the way he runs this very large JWST team. And it's really been a joy to work with him on that. And I want to just give you a little interesting fact about Anil. He triple majored in physics, astronomy, and music. Anil looks nervous. I'm not going to give anything embarrassing, but I think his instrument is the cello. It's been many years since I've met Anil, and I remember him telling me long ago at how he started playing the cello at a very early age with, a mom who's a piano teacher, I think.
Wow, your memory is good, Chavita.
And has insisted on him practicing. So he's an accomplished cello player who's played in various orchestras. So I'm really delighted to introduce Anil to you. And I'm also delighted to introduce to you Kameron Goold, who is a second-year graduate student in Anil's group, who's been working on the JWST data, really amazing dedication. And he's been interested in AGNs, chemical evolution of the Milky Way, and galaxy black hole coevolution. And an interesting fact about Kameron is that he has a previous bachelor's degree in business administration, which to me is like a really hard subject. And he's the owner of a company called 321 Click Photos. Is that right, Kameron?
Yeah, 321 Click. Like
321 Click. Oh, and yeah, clearly. And he's also was the store manager of a Starbucks. And he's had numerous leadership roles outside of astronomy. So he has a very interesting background. So with that, I wanted to welcome them to, and I'll turn it over to them.
All right. Thank you for the very nice introduction, Shavita. We are going to start here, and I can see on Kameron's whether it's working. So perfect. Looks like it's working. So I'm going to be introducing this ReveaLLAGN project, which is a JWST project to observe 7 nearby low luminosity AGN. And I'm going to kind of give the intro, and then Kameron's going to give you the fun part of the results about halfway through. We'll switch. So ReveaLLAGN is a really big collaboration of a lot of wonderful people, including many people on this call. So thank you for coming. I wanted to highlight the group here in Utah that's working on ReveaLLAGN. Kameron, who's kind of the first person who started working on it, and then also Mallory and David, who are starting to work on projects on ReveaLLAGN now. Mallory's a postdoc here, a postdoctoral fellow here, and David is another second year PhD student. So many of you may not know me super well because I haven't done a lot of AGN research. As should be to mention, I've mostly been concerned with black hole dynamical mass measurements. And my real motivation in starting this project was kind of related to this interest in black hole demographics. And in particular, that massive, we really don't know the massive black hole populations in low mass galaxies well. And now below about 10 to the 9 solar masses, we really have no idea what the black hole populations are in those galaxies. And yet those black holes are really critical for understanding the seed formation mechanisms. That's what this figure from Jenny's paper is on the left-hand side. It shows kind of how different seed formation mechanisms make different predictions about the black hole populations in low mass galaxies. And this is, of course, also really key to understand whether there's intermediate mass black holes in the universe. That's very much related to the formation question of how black holes form, which we don't understand. But if we do have intermediate mass black holes, we would expect to find them at the centers of low mass galaxies. There's also kind of unknown contribution of feedback from low mass black holes, and therefore some impacts on galaxy formation that could be interesting. Notably for future upcoming missions like LISA and Rubin, if black holes are abundant in low mass galaxies, they would be dominant contributor to LISA sources and also for tidal disruptions in Rubin. So I just wanted to quickly talk about my prior work on dynamical measurements, which were done mostly with adaptive optics, near infrared integral field spectra. So that kind of is part of the reason why I got interested in JWST. And we've been doing these dynamical measurements and shown that black holes are common in galaxies with stellar masses down to 10 to the 9 solar masses. And this is based on a very small sample of galaxies, the pictures of which are shown on the left there. We've also published the first dynamical detections below 1 million solar masses. And this is work done by former postdoc Mark Den Brock and Yu Nguyen, a former grad student, as well as collaborator Tim Davis. In addition, we found some black holes in weird places. We found that compact, massive star clusters around big galaxies also show big black holes, the biggest of which is about 20 million solar masses in about 100 million solar mass cluster. But we've also gone all the way down to the extreme of 100,000 solar mass black hole in a few million solar mass cluster in Andromeda, and everything in between. So what we think these objects are stripped galaxy nuclei, and it turns out there could be a significant fraction of all the black holes in the local universe could actually be in these stripped galaxies that are torn apart from tidal interactions with more massive galaxies. So this is an important contributor to the black hole populations at low masses. So part of the reason, a little while ago, I realized that there's not a lot more that we can do. Current instrumentation really won't allow us to significantly expand the sample of nearby galaxies where we can dynamically detect black holes. And even once THT and TMT and EHT come online, there is still going to be a challenge, which is that as we get to lower and lower masses, there becomes increasing ambiguity in the dynamical mass measurements of black holes. And that's what's shown on the left-hand side here with a plot of the radial dispersion profile of omega Sen with the black dots, and the red and blue models show two different models that fit the data equally well. One that has a lot of stellar mass black holes collected at the center of the galaxy, and then the other one, which has about a 50,000 solar mass black hole. And it's really hard to disentangle those two different possibilities as we get to lower and lower masses, and those black holes are more easily replaced by collections of stellar mass black holes. So, I think that kind of brings me to doing black hole demographics with AGN, possibly. So the plot on the left here shows a cumulative distribution of nearby bright galaxies, the Eddington ratios of those galaxies based on X-ray observations. And what you can see is that the typical galaxy is accreting at something like 10 to the minus 5 or 10 to the minus 6 of Eddington. So these are galaxies are very faint. They're most galaxies' black holes are very faint. The Milky Way's black hole is 10 to the minus 9 of Eddington. And so if you want to be able to do demographics with these black holes, you really need to be able to detect black holes down to low Eddington ratios and low luminosities. And this is especially true in dwarf galaxies, where they become increasingly hard to detect except at the highest Eddington ratios. So just at most a couple percent of galaxies, dwarf galaxies in the local universe, show evidence for AGN activity. So one of the cleanest indicators of AGN activity in local galaxies are X-rays, and I wanted to highlight this work that Brendan Miller and Ellen Galla did, which shows how kind of a method for inferring black hole demographics at low masses in low mass galaxies. And the left-hand plot here shows the observations. The black stars are detections, the open diamonds are upper limits as a function of galaxy stellar mass. There's this kind of, all the colored points are a simulation, but basically what they model that data, assuming some sort of relationship between the X-ray luminosity and the stellar mass of the galaxy, and an occupation fraction, which is what the bottom panel over here is showing you. And they get some constraints on the occupation fraction based on the data. And what you can see is that even though very few black holes at the low mass end are detected, that they get some constraints on the occupation fraction being non-zero from that modeling. I've actually, with my student David and Elena, been working on trying to expand this work a little bit and expand beyond just early type galaxies to late type galaxies as well. We've been reanalyzing Chandra archival observations with a new galaxy catalog, of nearby galaxy catalog that David constructed very painstakingly. And one of the early results from this is that we find the X-ray activity seems to be higher in early type galaxies than in late type galaxies at the same stellar mass. And Elena is kind of currently working on this, the full occupation fraction analysis of this. So one more thing I wanted to highlight before jumping into the JWST data is kind of my pathway to getting to proposing for JWST data in the first place, which was this finding of AGN emission from very low luminosity systems using IFU integral field spectra in the K-band. And what we found is that in general, there was a unexplained kind of red continuum that made lines weaker at the centers of most of the galaxies that we were looking at that had black holes in them. And this, we interpreted this potentially as hot dust emission from 1,000-degree dust, which we do see in higher luminosity AGN typically. And we found that if we decompose our IFU data cubes into both an AGN component and a stellar component, that we get this map on the right, which shows a very compact source, nearly coincident with the center in most of the galaxies that we looked at. And so on the left-hand side shows the kind of results of all of the analysis that my student Antoine Dumont did in 2020 paper, showing that at low Eddington ratios, we get some surprisingly high near-infrared luminosities, sometimes more than a factor of 10 more than the X-ray luminosities in these very low luminosity AGN. There's these higher data, the higher luminosity data is from work by Leo Bircher and this other paper that's down there, Mueller-Sanchez. And you can see that there seems to be maybe some trend with Eddington ratio where we see higher luminosities at lower Eddington ratios. And then that combined with the well-known correlation between the 12 micron luminosity and the X-ray luminosity suggests that the infrared is a great place to study AGN. And if the infrared is a great place to study AGN, JWST is by far the most sensitive instrument ever built for detecting AGN. The plot here shows the bolometric luminosity of an AGN versus redshift, and the lines on here show the translations of correlations between the bolometric luminosity and the luminosity of individual lines and 12 micron point sources with the appropriate instruments. And what you can see is that in the local universe, we can detect AGN well below the Eddington ratio for a solar mass black hole. And at high Z, we should still be detecting low luminosity AGN in massive galaxies for sure. And kind of, one shocking stat to me was that, a 10 kilosecond MIRI image gives you comparable depth using that 12 micron X-ray luminosity to the 2 megasecond Chandra deep field for detecting AGN. But there's a big but here, which is that we need to know what these AGN actually look like because there's lots of, unlike the X-ray, this is not a very clean measurement. There's lots of potential contamination from star formation and gas in the near infrared and mid infrared. So that is why that's the motivation for the ReveaLLAGN sample, which is to study some black holes that we really know are there, and we know they're accreting, we know their X-ray emission. And what we did was we started with a sample of black holes with dynamical mass measurements. So we have a good handle on their Eddington ratio and a wide range of black hole masses, and tried sampling, basically in this left-hand plots plane, a wide range in both dimensions. And at the same time, taking kind of the nearest, brightest sources that we would get really good spectra of. So you can see the sample as those 7 galaxies. I also have highlighted Cen and Sagittarius A star, which are both going to be observed in a very similar fashion, maybe already have been, with NIRSpec and MIRI. Here's the pretty pictures of those 7 galaxies. Of course, this includes EHT source M87 and maybe future EHT sources, 1052 and Sombrero, and a bunch of other pretty spiral galaxies. Our observations are basically provide us with high resolution continuous spectra from 1.7 microns to 25 microns. You can see we're using both the NIRSpec IFU in the two longer wavelength high resolution configurations, as well as the MIRI MRS, which is shown on the bottom here, which provides high efficiency observations out to about 20 microns and then lower efficiency observations at longer wavelengths. So the primary science cases here are, one, to characterize the spectral signatures of low luminosity AGN to enable detection in future JWST observations, essentially to potentially create templates that can be used to fit photometry or spectroscopic low resolution spectroscopic observations, high resolution spectroscopic observations at all redshifts. And hopefully we will be able to find emission line ratio and SED feature trends with both black hole mass and Eddington ratio using our wide range that we have in those parameters. And what's shown here are actually the first NIRSpec observations we've gotten, which are of M81. I show them not because they're at all processed in a good way yet, but that you can still already see that if you compare the orange line, which is an annular flux, to the blue line, that we're getting pretty clean continuum in these data with very few stellar features, which are very clearly visible in the orange lines, which are all those absorption lines are real and high signal noise. The second science case is, of course, understanding the structure of low luminosity AGN. We don't understand the structure of any AGN very well, but I think that's particularly true of low luminosity AGN. And once we have these kind of ReAF components at their centers, the SEDs of those components and then their resulting ionization can help. We can understand that better from the properties of the coronal lines in these systems. And then we can also disentangle synchrotron and thermal emission through SED modeling, as is shown in the right-hand panel here. So those are I'm going to hand it over now to Kameron. And I guess we could take a couple quick questions if people have questions before we switch over.
Any questions, anyone, or should we? Anil, I think we can just take questions at the end.
Good.
Awesome. Great. Thanks, Shabita, for having us, and thanks, Anil, for the opportunity to share some of the work that I've been doing. I'm going to share some first look kind of analysis of NGC1052 and the Sombrero galaxy, both in the mid-IR instrument using from JWST. We also have some free data from 7319, which is a Seyfert galaxy that we use to compare a few features later on.
Sorry.
Great. So the initial analysis that we've done and kind of the structure of the remainder of this talk is going to be focused on first the extracted nuclear spectra from these galaxies, identifying what lines are there, their measurements, and comparing them against each other and other literature values. And then we'll look at some line maps to investigate kind of the structure and patterns that we might find from different lines. So this is becoming probably my favorite plot. It's the nuclear spectra of NGC1052 in the blue, Sombrero in the red, both from our ReveaLLAGN sample, and then comparing that to NGC7319 in the black, which is a kind of a bright Seyfert galaxy. So there's some things that might jump out to you right away. Line features in our sample are wider than 7319. The SED has kind of different shapes at different wavelengths. There's a lot to kind of investigate and unpack here. So the first thing is that we did is just characterizing the lines through multi-Gaussian fitting. And you can see here an iron 2 line. It's one of the strongest iron 2 features that we have. And on the left is just a single Gaussian fit. On the right is our multi-Gaussian fit here to better approximate the profile of the line. Our Gaussians, I think it's important to say, don't relate to any physical features of an AGN. We're just using multiple Gaussians to best fit the profile of each line. Which comes in really handy because two features of note are neon 5 and oxygen 4, which are both key indicators of AGN activity. And in both Sombrero and 1052, these two line features are merged with lower ionization potential lines. Specifically, neon 5 overlaps with a chlorine 2 feature, and oxygen 4 overlaps with an iron 2 feature. So luckily we have this very high signal to noise iron 2 feature that I showed you before, and you can see on the right here. And what we do is we use that as the constraint when fitting and trying to measure neon 5 and oxygen 4. And so here we can see in the top plot, I've just got the iron 2 line in velocity space plotted up against the neon 5 chlorine 2 feature in orange and the oxygen 4 and iron 2 feature in green. And you can see that it's a pretty good representation of those low ionization potential features. And then on the bottom, you can see the full fit where we use iron 2 as a constraint, and the orange Gaussian in both of those is our kind of best fit for our neon 5 and oxygen 4 features. And so here what we're doing is we're just overplotting all these low to mid ionization potential lines in velocity space. This is for Sombrero. You can see that a lot of these lines have very similar profiles. I think to note is that there appears to have a blue shifted features. You can see kind of the extended features on the left side of the plot here. And then the right plot is our H2 lines, which, if anything, show maybe some red shifted features as they tend to kind of inch out to the right. And then this is our same thing for 1052. So these appear to be more symmetric than in Sombrero, which might be interesting to compare the reasons why. And one of the ways that we're parameterizing these widths is by measuring the full width half max of each of these lines. And so in this plot, you can see Sombrero's in red, NGC1052 is in blue, NGC7319 is in black. And for our sample, the full width half max is increasing with ionization potential. And just in general, our data sample has broader lines than NGC7319. Great. And so these kind of similar features are found in a recent paper, Armis 23. They have the full width half max versus ionization potential here on the right. And these are for emission features found in the nucleus of NGC 7469. And it's the slope is a little bit different, but the same trends are found. Great. So from there, what we've done is compared our neon 5 and oxygen 4 measurements to some literature values. So this is comparing the luminosity of our neon 5 feature to the luminosity of our oxygen 4 feature. And it falls in the same kind of relationship that we'd expect and is found in literature investigating galaxies of all different types. And I think just, if it's pretty obvious, but our neon 5 detection in Sombrero is one of the lowest luminosities that I've been able to find in literature so far. So this plot, what we're looking at is neon 5, which is indicator of AGN activity, and we're comparing it to other species of the same element, so neon 2 and neon 3. Neon 2 can be caused through star formation. Neon 3 is kind of found in both AGN activity and star formation. So our first plot here is neon 3 versus neon 5. And in Gorge in 2007, they have a pretty good relationship between these two across a wide variety of AGN type. Our very low neon 5 detection puts us way off to the left here. And the next two plots are just kind of to investigate whether that's an excess of neon 3 or neon 2, or if it's solely or predominantly caused by just a very low luminosity measurement of neon 5. So the middle plot we compare to neon 5 to neon 2. Again, we're kind of outside the norm here. And again, I think mainly because of our very low neon 5 measurement. And on the very right plot, we're comparing neon 3 and neon 2, where we find that we are no longer an outlier, but kind of fall well within the general grouping. So our neon 5 measurements are, I think an effective JWSTs, like amazing resolution and power. And what that's doing is just pushing us off these kind of well-documented relationships found so far. And this is just another one of those relationships. So this is some line ratios between neon 5 and neon 2 on the y-axis, and neon 3 and neon 2 on the x-axis. And this is generally used as like a AGN contribution plot, where the higher up you are, the more contribution from the AGN you have. We are off that trend, again, quite a ways. And based on the plots from the previous slide, we think mainly because of just a really low luminosity in our neon 5. So the next thing we did was to compare our neon 5 luminosity to physical parameters of black holes. We used the B catalog, the B2020 catalog. And the top plot, we're comparing neon 5 luminosity to black hole mass, which they derived using the M sigma relationship. And it's kind of hard to convince ourselves that there's a neon 5 to black hole mass relationship here. Which is interesting because there's been relationships written about the neon 5 luminosity and the black hole mass. So it'll be interesting to investigate that further. The next plot is about, we have our X-ray luminosity in the 2 to 10 keV range plotted against our neon 5 luminosity. And there's a tighter correlation here, which I think is pretty expected. Brighter X-ray luminosity, we'd expect some brighter neon 5 luminosity as it's a tracer of AGN activity. And then the B2020 catalog uses this X-ray luminosity to calculate an Eddington ratio. And so we just plotted a neon 5 to Eddington ratio here, and we can see that maybe Eddington ratio is a better predictor of neon 5 luminosity than black hole mass. Let's see, there's a question. How much neon 5 is missed using a small aperture? Yeah, so we do use a 1 full width half max aperture for our extracted spectra. And right now what we're working on is an aperture correction. It seems to be about a factor of 1.5 generally, to like a rough degree. Thanks, Patrick. So the next part, we'll be talking about line maps, and we used kind of 2 different methods here that we'll talk about and show you. So our first method is just using a single Gaussian fit in each spaxel to get velocity and dispersion maps. This works really well when it's a really high signal feature. And the other method we use is just a continuum subtracted integration of flux over our feature window to get our flux maps. And this is my very poor drawing on the bottom of how we do that. So we have our data cube where the front face is our 2D image of the AGN, and in the Z direction we have our spectra. And just we take our feature, we integrate that flux, and we get our flux map. And then what we also do is we take the continuum around each feature to make hopefully a PSF. And we're using 1052 for that right now, as it's very clearly more point source than Sombrero. Great. So here are some line maps using our Gaussian fit method. Chosen some H2 features and compared those to some kind of low to mid IP lines on the right. So we have H2 on the left, and we're looking at Sombrero here. In the middle is argon 2, and on the far right is our neon 3. And so the shapes here kind of look pretty similar. The velocity maps all kind of share the same blue shift, red shift, which is interesting. And then next up we have 1052. Again, an H2 map compared against argon 2 and neon 3. You know, here it's pretty, H2 has a much different, is traced in a much different shape. We're in different regions here, and argon 2 and neon 3 are pretty point source, and in the velocity you can see as kind of the intense blue shift and red shift areas, which seem to kind of correspond to where the twin jets in 1052 are aimed at, which is pretty fun and worth looking at more. Here we're using our integrated flux method, and what we're doing mainly is creating a PSF to do some corrections on our Yeah. Okay. So what we're trying to do is measure the extent to which these features are found in the nuclear spectrum and the nuclear maps here. How extended they are can tell us, are they predominantly being formed in the nucleus versus maybe contamination from star formation in the galaxy. So at the top is NGC1052. The first plot here is a map of the flux of neon-2. The middle plot is the map of our continuum around it. And the right plot is the CDF of a fractional light found. And this red dotted line just indicates where the half-light radius is or the effective radius is. And then we've plotted that on these flux maps. At the bottom is Sombrero. So, I mean, I think at first glance, you can clearly see the kind of like star pattern in 1052 is really classic JWST point source shape. Sombrero is much more diffuse and extended. So looking at this, trying to calculate a nice effective radius for these, there's a conflict here. So in blue are our continuum measurements of 1052. In green, you can see is the effective radius using WebPSF of a point source. There's some offset here, and then also at the low wavelength end, you can see that the 1052 continuum curve up, which we think currently is just some contamination from the galaxy. And so what we did, our current, best fit here is this orange line. And we are using that as our effective radius, but there's a little bit more comparison and analysis to do here before we're too sure if the WebPSF is, to find out why the WebPSF is off from our current continuum measurements. Awesome. So that's it. Here's a kind of a wrap up of things. Line characterizations. We've got line profiles, line measurements, and we've got comparisons to some literature of these measurements and some flux maps to kind of investigate the shape and extent of our features. So thanks for the opportunity to present this work to everybody here. My email's there in the top right, and thanks a lot.
Great. Thank you so much, Anil and Kameron, for that very nice talk. And so early after receiving the data, it's really an impressive amount of work. So let's give them a hand for this very nice work. And we can take questions. So I saw Travis had his hand up before Kameron.
Great.
Did. Travis, go ahead.
Anil, Kameron, thank you very much for a really awesome talk with a lot of really beautiful data. I think that you could get a little bit more information out of the kinematics if you try to perform a multi-component analysis like you did for the nucleus, because when you're looking at the line width and you're measuring that with single Gaussian, if you have a very bright, narrow component, and then you have that wind underneath, you're just gonna totally ignore it. So I think that you'd be able to pull out a little bit more outflow information for some of these ionized gas structures with a multi-component analysis.
Yeah, thanks. Yeah, I think one of the challenges has been that, the signal noise varies so much that, the way we're doing the multi-Gaussian fit is we're using some sort of, BIC criteria in order to determine how many Gaussians to fit. So we're changing that number of Gaussians as we go to different radii because the signal noise drops, it makes it so the interpretation is a little complicated. So I think that is kind of why we're using the single Gaussian, but we definitely understand. Yeah, I mean, I definitely understand that that's not that. If we had high, I think for the handful of lines where we have high signal noise across the full to be able to view, we could certainly do much better.
Thanks.
Any other questions, Stephanie?
Yes, thank you. I really enjoyed both talks. I have a question, and actually I was wondering, Kameron, if you, I don't know if you can show the slides again, but where you found a very different H2, the warm H2 map compared to the other maps. And I believe you mentioned something in passing about, I missed exactly what you said about the radio jet, but are you interpreting this as H2 tracing more like shock instead of like star forming?
Yeah, that's
emission?
that's a good question. And there's definitely a lot more analysis to do. In 1052, the kind of the radial velocity in argon 2 and neon 3, like thanks Neil, that line there, roughly traces out where the twin jets have been mapped in here. As far as the warm H2 regions, I haven't done much analysis or on that yet and what might be causing the shape there.
Oh, yeah, it's very intriguing. I wonder if there's some sort of, maybe instead of just shock, like some kind of cavity where, yeah, I don't know. I guess one could speculate how they, but it's very interesting. Thank you.
Vivian?
Yeah, thanks, Anil and Kameron. And I have a follow-up question on this slide as well. So do you have CO ALMA data for this galaxy that you can maybe overlay on top of the H2? I wonder if you would see any similarities between the warm molecular gas and the cold molecular gas, and if that could give you some hints on what might be causing that shape.
Yeah, we do have Tim Davis is leading a ALMA program for our sample galaxies. We don't have the data yet.
Okay.
So, I believe that we are getting one of the CO lines along with some continuum measurements in that proposal. I don't know if there's pre-existing. It's possible there's a pre-existing high resolution ALMA data here, but I'm not aware of that.
Okay, yeah, I mean, I think it would be really interesting when you do get the data to kind of line them up. That's what we see in 7469. So yeah, the molecular gas looking completely different from the low ionization gas. So yeah, cool. Thanks so much.
Can I ask, Vivian, is the molecular gas aligned is the H2 lines in the JWST aligned with the CO gas in ALMA?
For 7469, that's what we saw. I didn't plot the CO map in my paper, but I did look at the maps and then they look pretty similar.
Okay.
Great, thanks, Vivian. Patrick?
Yeah, on the same topic, we actually generally do see that even with Spitzer, that the warm H2 follows the CO. You can see it in NGC4258. You can even see it in the NGC7319 data from MIRI. So it's a general thing, and that's why the ionized gas doesn't follow the same distribution.
For pointing that out.
Also, Patrick, to follow up your message on the web PSF, I have been simulating. I mean, when I've been doing it, I've been simulating the here. I'll go down to that slide. I have been simulating this for MIRI observation, but it's for a MIRI imaging observation because I don't think you can actually simulate a MIRI IFU observation. And I thought that would I thought that they would be closer, even if the optics are a little different.
I'm sorry. My comment was for NIRSpec. I'm not sure about MIRI, but we find this is generally true that the PSF is a little bit bigger than web PSF gives. For NIRSpec, there's some reasons for that might have to do with optics, but also there's some concern that the reductions aren't quite where they need to be yet. So if you're using cube build from the pipeline, watch out for that as well, because it can make the PSF look bigger.
Okay, we certainly are. So yeah, thank you.
Thanks, Patrick. Prateek?
Hi, great talk. Can you please bring up your slide where you show the black hole mass correlation, especially the M sigma one? Yeah. So here probably I missed. So for the three objects, your estimates are using The black hole mass estimates are using what?
Yeah, so the black hole mass estimates here are coming from the B2020 catalog, which uses the M sigma relationship to estimate black hole mass.
But for Sombrero and 1052, we have dynamical mass measurements. So
Right. Yeah, that's what I wanted to know, if it is similar for all the cases. Yeah. Thanks.
Might I say something? Might I make a question or a point?
Yeah.
Yes, I'm back again to this H2 structure, and you see across the nucleus. I think it was in 1052. Yeah, right. I think that one thing that can be done, we can do, is already to compare with the dust maps, because when we have angular resolution, we resolve the dust in filaments. This looks very much like a filament. And we have the dust map of these galaxies. We can see, overlay how this dust, presumably is a tracing molecular gas, of course, could compare with. Of course, we should compare with ALMA, definitely, but I think we could also do with dust, because that contains everything, all the kind of molecules we might separate in AGN or CO or whatever H2 in dust is all there. So we could do that. It would be interesting.
Awesome. Yeah, definitely. Thanks.
And then with the kinematics, even you might have an inferring a bit of kind of inflow, perhaps, or whatever. If it's inflow.
Right. Awesome. I'll email you, and if you don't mind, and maybe I can get some of those papers where you have the dust maps, and I can do that comparison.
Yes, a comment.
It's actually a good idea to get imaging observations with NIRCam to get higher resolution dust maps than you can get from the IFU observations.
Did you do any of the MIRI free imaging with the MRS data as well? If you have MIRI continuum images, that's something that we've seen.
Yeah, they're not, we didn't take, we did the parallels, but haven't switched so that we're actually covering the nucleus with MIRI. So unlike your program, I think. So we do have, a lovely image of the outer disk of Sombrero.
That's good.
Any other questions? I have questions, but just want to see if anyone else has any questions. So I wanted to say actually that, these luminosities are unprecedentedly low. And just looking at your spectra, it's quite striking how they differ from, 7319, both in the equivalent width and the line luminosities. And, just kind of zooming out with what we've learned from JWST on all of these, NIRSpec and MIRI observations, I'm curious just to see how much the nuclear line ratios are changing in all of these different sources. And since we have goals people here on the call, I don't know if anyone can do that sort of zooming out and kind of synthesis, like, do these look very similar to each other? Because this is really the first time that liners are being looked at and that we have the sensitivity to detect these lines. And yeah, I'm really curious to see, are the line ratios for the higher ionization potential lines, like there's, I believe the magnesium 7, which is 188 or something electron volts, and the magnesium 5 ratio, that would, you don't have to worry about contamination by photoionization from stars. And I wonder if you looked at that ratio and we can compare it and goals, targets, and whatever is available right now to see, do we have really evidence for an intrinsic change in the SED as you go to these more radiatively inefficient accretion modes that we think is happening in liners?
I'll just say that, I think this plot is not due to contamination from from there's clearly point-like emission at the center of both galaxies. And I don't think the fact that this is an outlier is related to contamination, but is instead an ionization difference. So I think while like many of the previous observations, this might be this trend might be a mixing of star formation and AGN emission. I think here we're just seeing qualitatively different ionization.
But I don't mean in your points, but the other points
Yeah,
are
exactly.
from a big aperture, right?
Yes, for sure.
Yeah, interesting. Curious.
No, I
Yeah, I
think
think
that
our
the
biggest
so
problem-
sorry.
Oh, I'll just say one thing, like our biggest problem is really just finding good comparison data because there's so few, I guess there's, this one goals target, which we actually had just found out about last week, and then 7319.
Stephanie?
Yeah, so following on this topic, and so together with the different apertures and these line ratios, I was curious. My understanding is that neon 5 would come from the narrow line region, so not just the central. So are you resolving out the narrow line region in here, or do you assume that they're within, because it's such a low luminosity, is the narrow line region all within the PSF? Is that the assumption?
Do you want to?
No.
Okay, I think that we have, it's a little bit hard to say still, because if we had really good line maps for these emission lines, we can tell a little bit more just from the morphology of the line maps. But in neon 5, the signal noise is really low, essentially except in the nuclear spectrum.
Mhm.
There is, some. So it looks like the source is consistent with being point-like, I would say, for the neon 5 emission. Yeah.
Okay.
So
Thanks.
we're trying to quantify the radii of the flux maps, and that should give us some indication. It's pretty clear in both cases that it seems like surprisingly the neon 2 is more compact than the neon 3 emission. So there's some surprises there.
Yeah, that's very interesting. Okay, thank you. I look forward to seeing also more such low luminosity AGN. Maybe that will help.
Yeah.
Thanks.
Vivian?
Yeah, I just want to quickly follow on Shavita's point where, it'd be really interesting to compare, these low luminosity objects with the high luminosity objects. I was just telling Neil last week through my talk that we see the high ionization coronal lines in the Sievert-1 galaxy so far in the ERS program, but among the supermassive black holes in the other mergers, it's a lot murkier. We do not see coronal lines yet in the other mergers. So I mean, there might be Compton thick sources, right? That's an issue, but we do definitely want to have more resolved observations of the coronal lines in all of these sources, so we can compare across the demographics of black holes. So that'd be great.
Yeah. I actually have a quick question for you, Vivian. In the Armis paper, you interpreted the blue shifted lines as being due to an outflow. And I guess I'm a little surprised that I understand that if there's differential extinction, that on the red shifted and blue shifted side, that you would get preferential blue shifted emission. But I guess I'm surprised that there's sufficient extinction at 15 microns or something to make those kind of blue shifted lines. Did you guys talk about that at all, or kind of?
Yeah, I mean, we spent forever kind of trying to interpret the geometry of that system, really, and we have some higher, because in the optical ionized gas kinematics, I think we are all seeing only blue shifts as well, and so that kind of gives us some higher that we're a little bit biased into going into the system, thinking that we're expecting the blue shifted outflow coming at us. I will say that there is like high resolution OSIRIS data that goes into the central 100 parsec or something, where maybe you can interpret seeing like both sides of the line. And this was from Francisco's Will Sanchez paper. And the problem with that is that the field of view of Osiris is like within the pixel of our MIRI. So whether that's like the base of the outflow that we're seeing, or if it's something else. And then at the time, I think Francisco said he had yet to do the multi-component fit. So there's a little bit perhaps more work to be done to understand that. So I would say that's we did try to talk about it, and that's the best understanding we have reached at that point, but certainly really interesting system to spend more time in understanding.
Great.
Patrick?
Yeah, on the same topic, I think we should be open to the possibility that these are asymmetric systems. I mean, you can even see that if you look at NGC1052, that it doesn't look like the same on both sides of the nucleus. So should be open to that and not automatically jump to think that these are outflows. On the other hand, I see a predominance of blue shifts in these things that we've seen so far, and it's starting to concern me.
Yeah, I guess I just don't have a good sense of how I kind of assume that there's no extinction going on here, but yeah.
Speaking of extinction, can you say anything about the hydrogen recombination lines that were detected, and can you measure extinction in this and other sources?
We have not measured extinction using the hydrogen lines. But
now we just have the Humphreys. There's just this one Humphreys line.
yeah,
We don't have, when we get the NIRSpec data, we'll have there's a lot, but these are just the MIRI data. So I think we definitely will be able to do that, but not yet.
Yeah, that would be very interesting, and to compare, I guess, where you see the blue shifts. And any
If
other
I might-
unit? Oh, Almudena?
No, if I might say, regarding these coronal lines, I think your point about making these line ratios with coronal lines is super important. And mostly focusing on coronal lines, because these are really true traces of the activity, of the central activity. The problem is that these are the first liners that we are able to see these neon phi lines. With ISO, it was not possible. I mean, because they are low luminosity, the line gets completely swamped in the continuum. So we needed a little bit better spatial resolution. They came out. That's fantastic. But it turned out that lines, like you say, magnesium was very faint or not detected. I think Kameron, you have look at that.
yeah, that's right.
I think
Magnesium 5 hasn't been detected. Yeah.
Then of the two neon phi, one of them is also not detected or very faint, which is really a pity.
Yeah. The neon 5 at 24 microns is right where two channels meet, and so there's kind of a split in the spectra right now. So it's making measuring those really challenging and suspect.
It's pity because it would have been a good diagnosis for density, first density determination coronal line. And neon 6 is not detected.
That's right. Yeah.
And 4. I think that with the near spectrum, maybe there are other lines, coronal lines there, so we might have a chance, and then making a pure coronal line ratios it's hard also to compare with other galaxies that are no liners, because some of these lines are not well detected or have not been detected. But I must say, then usually high-end in Eddington sources, you see them as well.
Yeah.
So I think it should be pushed this thing. And then another thing I want to say, that this coronal line as outflow traces, I would say we did for a number of sources since in last few years, where we have very high angular resolution with adaptive optics. We trace the silicon cis line, which is a coronal line, and this line is really resolved, is outflowing. The coronal line, in addition, is a very nice tracer of radial motions. It's not subjected to rotation, but it's usually in radial motion. So it's a very good tracer for outflowing is how we interpret it. And we compare with radio data with jets. And in some cases, we nicely associate the blobs in coronal gas, in silicon seas, with blobs in the jet. So it seems that the jet impact the median and excited to produce coronal emission. You need high velocity, so it fits. So yes, they are really good traces of outflowing gas. There is also the work that Francisco Muller, I don't know if he's around, he found a similar thing too. So yeah, they are indeed.
Perfect.
Thank you, Almudena, and thank you so much, Anil and Kameron, for presenting this really nice work. So let's give them a hand one last time. And